Okay, it looks like we're live now. And let me just pop over and make sure that everything is running properly. Okay, it looks good. So just a quick update where we're at. So I've gotten to the end, and I'm using air quotes here, of problem 5. I decided that there was just a little bit too much of a gap between my understanding and what was being asked on the problem set. And I'm aware, I haven't gone through all of the material. I wasn't thinking that I was going to need to do too many different sets of problem sets. But I'm looking at what's going on with the problem sets, and I know there's a lot of material, a lot of problem sets that I can work through from various sessions of this, but they don't all have solutions. And because they don't have all solutions, I'm trying to be a little bit stingier about how I use the problem sets. I'm trying not to just kind of just rush through them and look at the answers right away, because then I've kind of missed my opportunity for feedback when I was ready. Now, I'm also trying not to do the opposite approach, which is to do a lot of like weird studying to kind of before doing the problem sets, because that's also going to have an issue. So it's been a little bit of a balance. And for me, in this particular problem set, I felt like, you know what, some of the stuff I didn't understand from the lectures in as much detail as I should have is coming into play here. And I was thinking, you know what, I'm going to go back, do a Feynman technique, kind of go through it step by step. And I was thinking I was going to do that after the problem sets, maybe even after I'd watched all the lectures. But now it's looking like it's coming into play. And you know what, I just think I'd feel better if I just went and did that now. So what I'm working on right now is a Feynman technique for, and quite a long name I've got right here, but I'm saying it's the brute force method for solving the partial differential equation for the harmonic oscillator, essentially the time evolution of the Schrodinger equation. So we have the wave function, and we want to know, in particular, we want to know what are the energy eigenstates of this function. And so I haven't done that much. I've just kind of started with just getting to the real basics, like remind myself, what's a harmonic oscillator? Why is it sort of an interesting system? And the two really, you know, from classical mechanics, the two really common systems that you think of for simple harmonic oscillators are the spring and weight system. It goes like this, and then the ball and pendulum. And they have been expressed in this format as basically that the amount of force that the object, in this case, this sort of pendulum thing, or this, that it experiences is proportional to its linear displacement. So you have, because force is equal to ma, what you have is essentially the second derivative is proportional to the position. So x double prime is proportional to x, and because you have that relation, a lot of it's a solvable differential equation, and a lot of stuff comes out of that. So now we're trying to figure out how can we do this for the wave function. Wave function is obviously more complicated because now we're not just talking about a single little fixed rigid ball, but this sort of complex valued thing that exists over all space that has various amplitudes and phases and this kind of stuff. And it is itself, that is that thing that is happening here. So now we're trying to solve that for this problem. So basically what I'm doing right now is I just started by, I wanted to read through in this quantum mechanics textbook, an introduction to quantum physics. I wanted to read through their full explanation of the harmonic oscillator. I may go into, this is a book that I had from the MIT challenge when I was doing classical mechanics, electromagnetism, Ohanian physics. And there might be something here about harmonic oscillators as well. I don't know how much I want to go into the kind of classic description of the harmonic oscillator, because we're mostly looking at the quantum case here, but I think I want to have definitely enough so that I can understand kind of what's going on, what's the motivation for doing certain things. So let's go back, and I'm just going to start by reading from start to finish without taking little intermediate breaks, start to finish their textual explanation, so that I can kind of get an overall sense of what we're doing. Then I'm going to go back to the Feynman technique, and then there's going to be probably a step-by-step as I go through and try to explain everything to myself. So where did we leave off here? Okay. think is this. It's a little bit too big for displaying in my camera radius. I have to work with a very small raising. It's even the size of my hand. There's not a lot of space here for reading these things. So I apologize if you can't see something that I'm doing. So I'll just read it. So given this single equation, our task is reduced to finding each value of E for which the associated wave function psi x falls towards 0 at large distances from the origin. I think we're talking about this here, yeah. So essentially what we need to have happen is we need to have it trail off to 0 at the edge. And so by trailing off to 0, we can ensure that the function is normalizable or square normalizable, because if it's not, it doesn't correspond to any meaningful interpretation. We can hope to find wave function psi, each of which has a single functional form over the entire range of x. To begin looking for acceptable functions of psi, we use an often helpful tactic. Examine the form of the wave function far from the center of force. What happens is a single analytic function psi for very large x, very deep into the region that is forbidden for classic particles. We can obtain a hint by recalling that outside the square well, the function decreases with distance according to the expression e to the negative alpha x, where the constant alpha is this 2m, the potential minus the energy to the power of 1/2 over h bar. For the harmonic oscillator, voltage V, I guess potential voltage, V increases as the square of x. So the decay of the wave function with distance is not a pure exponential. A crude way of describing this is to say that for the harmonic oscillator potential, the coefficient alpha is not constant, but increases with x. So the wave function tends towards 0 even more rapidly with the distance than the case of the square well. If we ask for the variation of alpha with x very large, given E, the answer is that alpha becomes linear in x. Constant x, large x. Therefore, in the limit of large x, we expect the harmonic oscillator wave function to approach 0 with the exponential square of the distance from the center of attraction. Okay. All right. So, you know what? How long is this section? I'm wondering whether I want to go... How long is the harmonic oscillator? This is not very long. It's only a couple pages. So I think I'm just going to read through the whole thing before I start doing the Feynman technique. Therefore, in the limit of large x, we expect the harmonic oscillator wave function to approach 0 with the exponential square of the distance from the center of attraction. This x dependence is encountered repeatedly in physics and is known as the Gaussian function. The standard Gaussian form results if we set the constant in the exponent equal to 1/2, 1 over 2a squared. Then the wave function at large x takes the form e to the negative x squared over 2a squared, where the constant a has the dimension of distance. The argument leading to equations 413 is a crude one, and the result must be verified by substitution into the Schrodinger equation. For regions far from the center of attraction, 4-11, which was this one up here, 4-11 becomes that this roughly equals why are we removing that? I guess just because the why are we removing the E psi? Oh, because we know that psi has, we're guessing that psi has this form, and far from the center, this is roughly equal to 0. So if this equals to 0, we can just ignore the constant term. Taking the first and second derivatives of psi from equation 4-13b, we have the spatial derivative of psi equal to negative x over a squared e to the power of x squared over 2a squared. Second derivative is equal to 1 over a squared e to the negative squared 2a squared plus x squared over a to the fourth. So this is equal to x squared over a squared e to the negative x squared 2a squared for large x. Substituting the last expression into equation 411, so this one here, and canceling the common exponential factors gives a squared over 2m x squared over a squared is equal to 1/2 cx squared. This yields an expression for the constant a to the fourth is equal to h squared over mc. Equations 416, 414 tell us that every wave function of the simple harmonic oscillator, one for each bound state energy, is dominated by the same exponential form in the limit of the large distance from the central force. Near the center of the force, the different wave functions must differ from one another, or they would not satisfy the Schrodinger equation for different values of energy. One way to indicate this difference is to multiply the Gaussian by a function of x that differs for different energies. We can say more about these multiplicative functions, but from our experience with qualitative plots, we know that since the simple harmonic oscillator potential is symmetric, the energy eigenfunctions must be alternately odd and even functions of x, with an even function for the lowest energy state. Since the Gaussian is an even function of x, each function that it multiplies must be odd or even itself. That multiplies must be odd or even itself. One kind of function that can satisfy all our criteria is a finite polynomial in x. Polynomial that is an odd function of x is easily constructed using only odd powers of x, while a polynomial that is an even function contains only even powers of x, possibly including a 0th power of x, which yields a constant term. Every polynomial with a finite number of terms is dominated at large x by the exponential Gaussian factor, so that at large x, the wave function automatically has the form e to the power of negative x squared over 2a squared if a multiplicative polynomial has a finite number of terms. So we just know, for instance, that the Gaussian overpowers a polynomial. Can you guys see here? I can't really see with my picture. You know, I'm going to switch just to straight desktop here, just so you guys can. Okay. Since by definition a polynomial contains only positive powers of x, the wave function will remain finite near the center of force, as it must to be physically acceptable. All right. For these reasons, we write the SHO, simple harmonic oscillator wave functions, in the form psi is equal to f n of x multiplied by e to the negative x squared over 2a squared, where f of n is a polynomial whose highest order term is proportional to x to the n. The single analytic function psi x holds over all values of x, both inside and outside the well. The polynomial consists of either odd powers of x or else even powers of x with maybe an additive constant. Now one can search systematically for polynomials such that psi x in the equation 4-17 satisfies the Schrodinger equation for the simple harmonic oscillator. This is done using polynomials with undetermined coefficients and letting the substitutions into the Schrodinger equation 411 determine the coefficients and the quantized values of energy for each valid wave function. The result is a set of polynomials known as the Hermite polynomials, symbolized Hn and named after Charles Hermite. Hermite, I guess it's Hermite. Hermite, a 19th century French mathematician. Yes, it's Hermite. Charles Hermite. The complete wave function consists of an Hermite polynomial multiplied by the Gaussian exponential function and by an appropriate normalization constant. Table 4.1 lists several SHO energy eigenfunctions. Here we shall carry out the procedure of determining the coefficients for the wave function of the two lowest energy states. Shall find only the form of each wave function. The normalization constants are easily calculated. See the exercises and are included in table 4.1. The procedure is simplified by substituting the constant a to the fourth is equal to h squared over mc from equation to obtain negative a to the fourth, the double spatial derivative in psi plus x squared psi is equal to 2e over c. And then we have some things here. Is this the end of it? No, we've got one more thing. The wave function for the lowest energy in a symmetric well must be even. The simplest even polynomial is a constant. Therefore, try the Gaussian function alone for the lowest energy wave function. For historical reasons, the lowest energy state in the harmonic oscillator is given the quantum number n equal to 0 rather than 1. This convention n is the highest power of x in the polynomial n and is also the number of nodes in the wave function. Okay, we knew that. Psi naught is equal to e to the negative x squared 2a squared. Although this form of the wave function arose as an approximation at large x for all simple harmonic wave functions, we shall now show that it satisfied the Schrödinger equation exactly for all values of x in one case, that of the ground state. The second derivative of this function is given in 4-15. Substituting for psi and d squared psi second spatial derivative of psi in the Schrödinger equation 4-18 and canceling the common exponential factor, we have a squared is equal to 2e naught over c. And this gives a value for the permitted energy E0. Making use of the expression for a from 4 to 16, we now have E0 equals 1/2 c a squared equals 1/2 h bar over the square root of c over m. Now, square root of c over m is the angular frequency corresponding to the classical harmonic oscillator. Classically, this angular frequency is independent of the amplitude of oscillation and therefore independent of energy. In quantum mechanics, omega naught does not have such an obvious physical interpretation. However, we can use it as a parameter for E0. E naught is equal to 1/2 h bar omega. You can easily show, see the exercise, the distance a, which defines the characteristic width of this lowest energy wave function, which appears in the exponential factor of all simple harmonic oscillator eigenfunctions is equal to the maximum displacement x0 of the classic oscillator of this same energy E naught. This convention, n is the highest power. Okay, so this is footnote. In summary, for the lowest energy state of simple harmonic oscillator, we have this Gaussian, and the energy is equal to 1/2 h bar omega, where omega is equal to the square root of c divided by m, and 1 over a squared is equal to the square root of mc divided by h bar, or m omega naught over h bar. The second energy level, n equals 1, must have an odd wave function with one node, but every odd function has a node at x equals 0. The simplest odd polynomial with only this one node is x itself. With this polynomial factor becomes this. Taking derivatives, substituting the Schrödinger equation, and canceling common factor yields the equation. In occasions, you will try the following form for the third energy level. 1 plus bx squared. Notice you'll obtain the energy E equals 5/2 h bar omega, as well as the necessary value of b. The first 5 harmonic oscillator wave functions properly normalized are given in table front. It is striking that although the wave functions psi, nen, x are complicated, the permitted energies are given by a remarkably simple formula, n plus 1/2 times h bar omega naught, where n is just a positive integer, or just in, positive energy, I guess 0 count. Note that the energy difference between any two successive levels in the harmonic oscillator is just h bar omega equals h, I guess v, the classic frequency, and nu, I guess, is that later, of the oscillator multiplied by Planck's constant. This equal spacing of the levels is a unique property of the simple harmonic oscillator. It's the 0-point energy. We have followed a common procedure used by scientists who have already solved a lot of problems. In a situation, they make an informed guess at a solution. Okay. So let's try a first pass at kind of the rough Feynman technique, and then let's go through the class notes with Barton Zwebeck to fill in some of the gaps, because this was something that was, this seems a little bit simpler than what he said in the class. So comparing to the genetic, and this represents the potential energy in the system. In the classical case, omega naught is the characteristic frequency of the system and is, I guess I should put angular, independent of energy. Like parabolic, is that the right word? Parabolic well. In the classical case, it would reach some speed and start all down. derivation. Continue. Without friction or damping. Function psi in the classical case. Particle go here. Just try it. We know from the infinite well, square well. Where well the drop off for particle exponential however area the it's just deeper and deeper. I should say it's deeper and deeper. x. Therefore, a Gaussian function is a better approximation of far off zones in the sickly disworld region. All right. What was our Schrodinger equation again? We have E psi is equal to H bar over 2m I think that's right. Let me just see what the Schrodinger equation is. I just want to make sure I'm not writing it down wrong. Negative. All right. Yeah. Negatives. This is 1/2 C. 1/2 C. So if we put in at x X is far from our Gaussian quickly goes to 0. So for large X behavior and ignore this term. So let's go through here and see how they actually calculate this. So they go okay. Actually, we don't need to have this here because we're not. This term. Therefore, we can say regardless of the particular energy state, the X is dominated this Gaussian. However, we know a simple Gaussian alone cannot give us all states because it must print behavior near the center. we know one guess for what kind of extra function we could insert is Fn where this is some polynomial of power x order of order n. A reason this is a good guess is that Gaussian dimensional will always overpower finite polynomial. Another guess we could make would be that polynomials be either even or odd. If this were not true, the wouldn't respect symmetry. And a more constrained the HN or Hermitian polynomials are Yeah. J is not even. I think I'm going to get rid of this part here, because these Hermitian polynomials are not necessarily what we're looking at. So ground 8 fit with just Gaussian. So we go psi I believe this is negative x squared. I'm not sure actually. Let's let's go over here and try. All right. Primitive. Meets functions. derivative of the Gaussian is equal to x oh, here we go. I have it here. It's written down right here. Okay. So this is equal to x over a squared negative x squared over 2a squared, and then so if we have this wave function, all right, can we get this value here? Well, we can cancel the common exponentials. Right. Into Schrodinger and cancel out Gaussians. Then we get E is equal to m over a squared plus x squared over a to the fourth plus 1/2 c x squared. 4D canceling, we have equal to how are we getting this here? So we get E minus A squared. We try to solve for X or H? I'm not quite sure how they arrived at that. All right, let's go back because maybe I'm skipping over some part of the derivation. Or something's getting substituted here. All right. $4.15. Okay. One half A squared is okay, so I missed something here. 416A. Hold on a sec. Let's go this here. It's tricky to find space. Okay. So X behavior and get and fourth. So if we have x squared over a to the fourth equal to 1 h bar. What do we get for this? So how can we leverage this? Well, let's see what is it? So a squared is going to be this square root. So I want to see how they're canceling this. What am I missing? I'm not sure how they're getting this expression to cancel. Now let's go back. Try it again over here. So let's just do some math to figure this out. With the squared, right? Yeah. I'm forgetting a factor of squared here. How the heck are we getting that? So if we look at the Schrodinger equation, where's our Schrodinger equation? squares here. And then this is going to be a minus x squared plus x equals 2b over c. Yeah, all right. This is tricky because I'm not sure. 418. Okay, I'm missing a front. Here we go. Okay. So hold on a second. All right, so we can take this and take the Schrodinger equation. And we can get Schrodinger equation is h bar squared over 2m minus squared psi dx plus squared psi equals e psi. So we can have negative a to the fourth So then we can just take C and C divided by C multiplied by 2. How are we getting rid of the factor 2? Oh, there's a 2m under this. All right, so then we have negative a to the 4. And now we want to I do drink coffee, but I haven't had any since this morning. Where are we here? Okay. So we have this, which is what I have in the book. So just copy it from there. Now we want to sub in these equations. And so the equations were, it's negative a to the 4th times 1 over a squared All right. And so we can cancel, and we get minus a squared plus x squared, minus x squared plus x squared equal to 2e over c. These cancel, 2e over c is equal to negative a squared. We must have dropped a minus sign. So dropped a minus. Yeah, minus. This is plus. Oops. So this is there we go. All right. Now from this we can see E0 equal to 1/2 CA squared, which is equal to 1/2 H bar C over M. All right, now we want to figure out the same for this with these functions. They don't really do as much here as he did for figuring out these functions. So where do we have? For n equals 1, can try a simple 1 degree polynomial x e to the negative x squared over 2a squared. All right, and then so let's try that again where we had the so try putting into Schrodinger equation what do we get here? Again, we get minus a. Then is the second derivative. What is this going to be equal to? E to the negative x squared 2a squared plus is going to be equal to what? That's going to be equal to... Plus... This is going to be a big mess. All right, let's not insert it all in there. Is it 5? Two plus 1. Okay. Put this back here. So, let's go back to the lecture where that happened. Okay, I'm going to go through his method and see if I can't make better sense of it going slowly. So this was from lecture 8. So I'm just going to open up that window. I think I want it to be, yeah, like this. No, I actually have to have a different window here. Hold on a second.
The following content is provided under a creative.
So let me just select the screen. All right.
Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free donation. Materials from hundreds of MIT courses. Visit MIT OpenCourseWare at ocw.mit.edu.
Today, we do a harmonic oscillator. And before getting to the harmonic oscillator, I want to touch on a few concepts that have been mentioned in class and just elaborate on them. It is the issue of nodes and how solutions look at, and why solutions have more and more nodes, why the ground state has no nodes, this kind of stuff. So, so these are just a collection of remarks and an argument for you to understand a little more intuitively why these properties hold. So, one first thing I want to mention is if you have a Schrödinger equation for an energy eigenstate, Schrödinger equation for an energy eigenstate, you have an equation of the form minus h squared over 2m d second dx squared psi of x plus v of x of bound states. Now, what is a bound state? A bound state is something that is not extended all that much. A bound state will be a wave function that goes to 0 as the absolute value of x goes to infinity. So it's a probability that certainly doesn't extend all the way to infinity. It just it's normalized. You're looking for bound station, and your difficulty is that you don't know psi either. So you have to solve the problem if you were thinking, oh, this is just a value of E, we know the potential just calculated. That's not the way it works in quantum mechanics, because you need to have normalizable solutions. So at the end of the day, as will be very, very clear today, it gets fixed. You cannot get arbitrary values of E's. So to make a couple of rules of this equation is that can't happen. V of x, certainly, if V of x is a smooth potential, then if you observe that the wave function vanishes, the derivative of the wave function vanishes at that point, these two things imply that psi of x is identical, and therefore it means that you really have that psi equals 0 at the particle. So what I claim here is that if the subpotential is smooth, the derivatives of it, and then the unit function is at that same point, then the wave function vanishes. Complete half a wave function of psi of x that does the following: it comes down here and down. This is not allowed. If the wave function is do this, it's going to hit an angle.
Here to try to get to the point where he starts talking about the oscillator, because I'd rather rewatch this entire lecture. I want to focus on the points that I don't understand. So he's just talking about the node theorem here, which I've already covered and I feel like I understand. So let's just zoom ahead. Just talking about bound states. Oh.
100% rigorous, but fairly nice and really physical, that I'm going to present to you why this result is true. So let's try to do that. So here is the general case. I'm going to take a smooth v of x that x.
This is just explaining why we're going to have some function like this. It's going to have these sort of nodes and whatnot. But I want to get to where he starts talking about the solving the quantum harmonic oscillator. There we go.
Is actually put pi over the period of an oscillation, and this you know from classical mechanics. If you have a harmonic oscillator of this form, the characteristic of the harmonic oscillator. Well, the energy operator is p squared over 2m plus we write 1/2 m omega squared x squared, where omega is this omega that we always think of an angular velocity or angular frequency. It's more like angular frequency. Omega has units of 1 over time. Is actually 2 pi over the period of an oscillation. And this you know from classical mechanics. If you have a harmonic oscillator of this form, yeah, it actually oscillates with this frequency. And E is the energy operator. This is the energy of the oscillator. So what defines the oscillator is something in which the potential energy, this term, is V of x. V of x is quadratic in x. That is a harmonic oscillator. Then you arrange the constants to make sense. This has units of energy because this has units of length squared, 1 over time squared. Length over time is like velocity squared times mass is kinetic energy. So this term has the units of energy. And you're good with that. And why is this useful? Because actually, in any sort of arbitrary at the minimum as a quadratic potential. It fits the potential nicely over a good region, and therefore when you have two molecules with a bond or something oscillating, there's a potential that has a minimum at the equilibrium position, and the oscillations are governed by some harmonic oscillator. When you have space-time traveling, there is a set of harmonic oscillators that correspond to photons. Many applications, endless amount of applications for the harmonic oscillators. Understand this system quantum mechanically. And what does that mean? Is that we really want to calculate and solve the Schrödinger equation. This is our first step in understanding this system. There's going to be a lot of work to be done even once we have the solutions in the equation. But the first thing is to figure out what are the energy eigenstates or the solutions of the Schrödinger equation for this problem. So notice that here in this problem, there's an energy quantity. Remember, when you have a Hamiltonian like that, and people say, so what is the ground state energy? Well, the ground state wave function, I have to do things, give me an hour, I'll find an approximate value. Dimensional analysis will do it. Roughly, what is it? Well, with these constants, how do you produce an energy? Well, you remember what Einstein did, and you know that h bar omega has units of energy. That's an energy associated with this Lagrangian, energy-like quantity. And we expect that that energy is going to be the relevant energy. And in fact, we'll find that the ground state energy is just 1/2 of that. There's another quantity that may be interesting. How about the length? How do you construct the length from these quantities? Well, you can start doing m omega h bar and put powers and struggle. I hate doing that. I always try to find some way of doing it and avoiding that thing. So I know that energies go like h over h squared over m length squared. So I'm going to call the length a quantity a. So ma squared, that has units of energy. And you should remember that because energy is p squared over 2m, and p by de Broglie is h bar over some lambda. So h bar squared, lambda squared, and m here, that's units of energy. So that's a length. On the other hand, we have another way to construct an energy is with this thing, m omega squared length squared. So that's also m omega squared a squared. That's another energy. So from this equation, I find that a to the fourth is h squared over m squared omega squared. And it's a little complicated. So a squared is h bar over m omega. So that's a length squared. I don't want to take the square root. We can leave it for a moment there. But that's important because that's a length scale. And if somebody would ask you, in the ground state, how far is this particle oscillating? You'll say, probably about a square root of this would be the natural answer, and probably about right. So, okay, energy and units is very important to begin your analysis. So, what is the Schrödinger equation? The Schrödinger equation for this thing is going to be, of course, minus h squared over 2m d second psi dx squared plus the potential 1/2 m omega squared x squared psi is equal to e psi. And the big problem is that I don't know psi and I don't know e. Now, there's so many elegant ways of solving the harmonic oscillator. You will see those next lecture. Alan Adams will be back here, but we all have to go through once in your life through the direct, uninspired method of solving it. Because most of the time when you have a new problem, you will from fairly difficult to be unpleasant by the presence of what kind of equation is that with all this constants. So this is the first thing up the equation. We have to put
understanding force as presented lecture 8.
well, you know, a nice function like y double prime is equal to y units. The derivative